Today we're going to talk about speed of waves again, but today we're going to focus on light waves. Before we get to light waves, a quick reminder, sound waves, longitudinal pressure waves, we're trying to see how fast sound traveled, and we saw that sound traveled way slower than light. It's important to realize that even though we think of light as instantaneous, it does take time for light to travel. It's just that it travels so quick that our everyday experiences on Earth, we don't notice that it does take time. But on larger scales, as we'll see today, the time can be pretty significant. So the lightning strikes, we think of everybody seeing the light at the same moment, but that is not true. We saw that sound depended on the material that it was traveling through, and with air, sound required us to know the temperature to get an exact value for the speed of sound. Today, we want to talk light waves. I want to remind you that light waves are caused when a charge moves. The electric field surrounding the charge is going to react as the charge oscillates or accelerates. It's going to create a pulse in that electric field that's going to travel outward from the source. This again is a radio station oscillating its electrons. It creates a light wave that can then be picked up by electrons in an antenna at your house or in your car. Again, it does take time for the light wave to travel, but it's such a small amount of time on a small distance like we have here on Earth that it's almost not noticeable. So this would be an example of a light wave where we have a transverse wave. And again, the light wave is going to be traveling at really high speeds. The oscillations for the light wave are just oscillations in the electric and magnetic fields. It is not a matter wave, so light can travel through outer space, obviously. Remember, when we use the word light, don't be restricted to stuff human beings can see. Light can come in a lot of different forms, and only one of them is called visible. We break the visible up into the red, orange, yellow, green, blue, violet, but realize there are also light waves called radio waves, microwaves, infrared, ultraviolet, X-ray, gamma rays. Okay? They're all light, and they all travel in a very similar way. All right? Origin of light waves, don't forget, it starts with an oscillating or accelerating charge. Remember that light can travel through space. It does not require material to carry it. In fact, matter just gets in the way. So light is going to travel fastest in outer space, and it's going to travel slower when there's things in its way. So when you're trying to find the speed of light, if you have your reference sheet, you'll have these numbers. They're called indices of refraction. And the bigger the number gets, the slower light travels. So for a vacuum, your index of refraction is 1. That's the smallest number you'll ever have for an index of refraction. And that means light's going to travel at its fastest possible speed. And that speed is 300 million meters per second. We give that the symbol C for the speed of light in space. And then the speed of light anywhere else, you take that number and divide by the index of refraction. So if it was water, we'd use an index of 1.33. And you just take the speed of light in outer space, divide by 1.33, and that's how quickly light travels through water. Okay, to show you guys how quickly light travels, here is a scale model of the Earth and the Moon, and this little thing is a beam of light. And look how quickly light travels between the Earth and the Moon. Literally a little more than 1 second, like 1.2 seconds to travel that distance. Not instant. It does take time, but it gets there awful quick. Remember when we sent humans to the moon, it took 3 days for them to travel. And that was the fastest humans had ever traveled. And light can do that distance in a little over 1 second. Okay, when we start to get on bigger scales and we look at light traveling from the sun to the different planets, well, by the time you get out to Neptune, believe it or not, it takes light a whopping 4.1 hours. It shows you how darn big our solar system is. That even at the fastest possible speed from the sun to Neptune is 4 hours. If we go out even farther beyond Neptune, we get all these Kuiper Belt objects like Pluto and Eris, and the farthest one out, Sedna, okay? And we just see it as a tiny little dot out there, but it's actually like almost like a Pluto-like planet. And it takes actually 70 hours, more than 2 days, for light to get out to Sedna from the sun. It shows you how big our solar system is. A light beam would take almost more than actually 2 days to get out there. When we look at Alpha Centauri, which is the closest star to the sun, it's the closest star to us other than the sun, and we look at how far away it is and we do a little bit of math, we find that it takes 4.2 years for light to get from Alpha Centauri to the sun. Realize that also means that it would take 4.2 years for light to get from us to Alpha Centauri. So if there's an advanced civilization on a planet going around Alpha Centauri and they look back at the Earth, they see us 4.2 years ago. They are unaware of all the nonsense that has happened in the last 4 years on our planet. That would not have occurred for them. They wouldn't have seen it yet. The light carrying that information out to Alpha Centauri hasn't reached them yet. Okay, Orion Nebula. You can go out and see this at night. Okay, if you find the constellation Orion right below the belt, you'll see the nebula. And in that nebula, if you have a nice telescope, you might be able to see that it's composed of dust and gas. And with a telescope like the Hubble, we can see that new stars and planets are being born inside that nebula. When we do a little bit of math, we find out that the light takes over 1,000 years to reach the Earth. So if you were to go out and look at them tonight, you would not be seeing them how they look today. You'd be seeing them how they looked 1,000 years ago. 1,000 years ago is how you're seeing these. We won't know for another 1,000 years how they're going to look tonight. Okay, what they're actually looking like right now. The information is going to take 1,000 years to reach our planet. Crab Nebula. Back in 1054 AD, humans all over the world recorded a star exploding in the sky. Now, when we look at it, we can see the remnants of that explosion. But when we do the math, we can see it didn't explode 1,000 years ago. Based on how far away it was, it exploded 6,000 years before today. So 5,000 years before they saw it, it actually exploded. So for 5,000 years, it was up there in the sky. Nobody knew any better, but that star had actually ceased to exist. It took 6,000 years for that light to reach the Earth and for us to see that the star was no longer there. The closest galaxy to our own, the closest galaxy to the Milky Way is the Andromeda. It is really, really, really far away, but with a good telescope you can see it. And believe it or not, you're seeing it the way it looked 2.5 million years ago. All of human history would have happened, and then some, during this time frame. So if there are creatures in the Andromeda Galaxy with technology enough to look at our own galaxy and pick up information about the planet Earth, they don't yet know about any of human recorded history. It hasn't happened for them yet. The light from the Earth won't reach them for almost 2.5 million years. And then the most extreme examples, when we look at quasars in deep, deep space, we see that it takes them 2.4 billion years for their light to reach us here on Earth. So when we see them today, we're not seeing them as they are today. We're seeing them as they existed 2.4 billion years ago. So anyway, that's some things about light. I'm going to ask you guys to answer a few questions online, share your notes with me, and then next week we'll actually do some math problems with speed of light. Good luck.